Analyze how the optimal solution changes if the problem is changed after solving a LPP. Systematically study the change in solutions. 1. If the objective function changes. 2. If resources available change. 3. If a constraint is added to the problem. Introduction. Let us commence this module by discussing the finding the optimal solution to a linear programming model is important, but it is not the only information about what is available. There is a tremendous amount of sensitivity information where the data values are changed. Sensitivity analysis is a systematic study of how sensitive the solutions are to small changes in the data. Let us start this module by understanding the sensitivity analysis. Suppose we solve a linear program by formulating an optimal table or simplex tableau. An optimal tableau has all non-negative values in last row, all non-negative right-hand side values, and a basis identity matrix embedded. To determine the effect of a change in the data, we will try to determine how that change affects the final tableau and try to reform the final tableau accordingly. Changing the objective function. The first change we will consider is changing a cost value by delta in the original problem. We are given the original problem and an optimal tableau. If we had done exactly the same calculations beginning with the modified problem, we would have had the same final tableau except that the corresponding cost entry would be delta lower. This is because we never do anything except add or subtract scalar multiples of rows 1 through m to other rows. We never add or subtract row 0 to other rows. Example 1. Maximize 3x plus 2y subject to x plus y is less than or equal to 4, 2x plus y is less than or equal to 6, x, y are both greater than or equal to 0. The problem has the following optimal tableau after adding S1 and S2 as slacks to place in standard form. So we have the matrix which is given. Let the cost for x be changed to 3 plus delta in the original formulation from its previous value 3. After doing the same operations as before, that is the same pivots, we would end up with the tableau which is given. Now this is not the optimal tableau as it does not have a correct basis. For example, look at the column of x. But we can make it correct in form while keeping the same basic variables by adding delta times the last row to the cost row. This gives the tableau which again has been indicated. Note that this tableau has the same basic variables and the same variable values except for z that our previous solution had. Does this represent an optimal solution? It does only if the cost row is all non-negative. This is true only if 1 minus delta is greater than equal to 0 and 1 plus delta is greater than equal to 0. This holds for delta lying between minus 1 and 1. For any delta in that range, our previous basis and variable values is optimal. The objective changes to 10 plus 2 delta. Let us take another example where we change the cost of a non-basic variable. In the previous example, we had changed the cost of a basic variable. Example 2. Maximize 3x plus 2y plus 2.5w subject to x plus y plus 2w which is less than equal to 4, 2x plus y plus 2w which is less than equal to 6 where x, y and w are greater than equal to 0. Again, the optimal tableau is given. Now suppose we change the cost on W from 2.5 to 2.5 plus delta in the formulation. Doing the same calculations as before will result in the tableau which is given. In this case, we already have a valid tableau. This will represent an optimal solution if 1.5 minus delta is greater than equal to 0, which implies that delta is less than or equal to 1.5. As long as the objective coefficient of W is no more than 2.5 plus 1.5, which is equal to 4 in the original formulation, our solution of x is equal to 2 or y is equal to 2 will remain optimal. The value in the cost row in the Simplex tableau is called the reduced cost. It is 0 for a basic variable, and in an optimal tableau, it is non-negative for all other variables for a maximization problem. We can see that after changing objective function values in the original formulation will result in a changed cost row in the final tableau. It might be necessary to add a multiple of a row to the cost row to keep the form of the basis. The resulting analysis depends only on keeping the cost row non-negative. Right-hand side changes. For these type of changes, we concentrate on maximization problems with all greater than equal to constraints. Let us take an example to understand this. Maximize 4x plus 5y subject to 2x plus 3y is less than equal to 12, x plus y is less than equal to 5, and xy is greater than equal to 0. The optimal tableau after adding slack S1 and S2 is mentioned. Now suppose instead of 12 units in the first constraint, we had only 11. This is equivalent to forcing S1 to take on value 1. Writing the constraints in the optimal tableau longhand, we get Z plus S1 plus 2S2 is equal to 22. Y plus S1 minus 2S2 is equal to 2. X minus S1 plus 3S2 is equal to 3. If we force S1 to 1 and keep S2 at 0, as a non-basic variable should be, the new solution would be Z is equal to 21, Y is equal to 1, and X is equal to 4. Since all variables are non-negative, therefore this is the optimal solution. In general, changing the amount of the right-hand side from 12 to 12 plus delta in the first constraint changes the tableau to what has been indicated. This represents an optimal tableau as long as the right-hand side is all non-negative. In other words, we need delta between minus 2 and 3 in order for the basis not to change. For any delta in that range, the optimal objective will be 22 plus delta. For example, with delta equals 2, the new objective is 24 with y equal to 4 and x is equal to 1. Similarly, if we change the right-hand side of the second constraint from 5 to 5 plus delta in the original formulation, we get an objective of 22 plus 2 delta in the final tableau as long as delta lies between minus 1 and plus 1. The most important concept in sensitivity analysis that emerges here is the shadow price of lambda I star of a constraint. If the right-hand side of constraint I changes by delta in the original formulation, the optimal objective value changes by lambda I star delta. The shadow price lambda I star can be found in the optimal tableau. It is the reduced cost of the slack variable Si. So it is found in the cost row 0 in the column corresponding the slack for constraint I. In the above case, lambda star 1 is equal to 1 found in row 0 in the column of S1 and lambda star 2 is equal to 2 found in row 0 in the column of S2. The value lambda I star is thus the marginal value of the resource associated with constraint I. For example, the optimal objective value, currently 22, would increase by 2 if we could increase the right hand side of the second constraint by delta equal to 1. Thus, we can say that the marginal value of that resource is 2. That is, we are willing to pay up to 2 to increase the right hand side of the second constraint by 1 unit. The conclusion of the above is that changing the right hand side of a constraint is identical to setting the corresponding slack variable to some value. This gives us the shadow price, which equals the reduced cost for the corresponding slack and the ranges. Adding a constraint. If a new constraint to a problem is added, there can be three possibilities. 1. The current optimal solution satisfies the new constraint. Second, the optimal solution does not satisfy the constraint, but the linear program still has a feasible solution. With the addition of a new constraint, the linear program does not have a feasible solution. There is a need to identify and deal with these kind of changes. Let us take an example to study all the three possibilities. Example 4. Maximize P equal to 60x plus 30y plus 20z subject to 8x plus 6y plus z, which is less than equal to 48. 4x plus 2y plus 1.5z, which is less than equal to 20. 2x plus 1.5y plus 0.5z, which is less than equal to 8. Solution. Adding slack variables and solving. 8x plus 6y plus z plus s1 is equal to 48. 4x plus 2y plus 1.5z plus s2 is equal to 20. 2x plus 1.5y plus 0.5z plus s3 is equal to 8, where x, y, z, s1, s2, s3 are all greater than equal to 0. The objective function becomes minus 60x minus 30y minus 20z plus 0s1 plus 0s2 plus 0s3 plus p equal to 0. Putting this in the matrix form is what has been indicated. By pivoting the final tableau, it becomes as indicated. The optimal solution is x is equal to 2, y is equal to 0 and z is equal to 8, and the objective function is 280. Now let's add the constraints. Case 1. Adding the constraint x plus y plus z is less than equal to 11. We will substitute the optimal solution in this constraint and check whether it is feasible or not. The optimal solution is x is equal to 2, y is equal to 0, z is equal to 8. So we see that 2 plus 0 plus 8 is less than equal to 11. Since the current solution is still feasible, therefore it is optimal. Case 2. Adding the constraint y is greater than equal to 1. This constraint does not satisfy the optimal solution. However, it is feasible. Thus, a new row is added to the tableau. The constraint becomes y is greater than equal to 1 minus y is less than equal to minus 1 minus y plus s4 is equal to minus 1. The tableau becomes as has been indicated. After pivoting the final table, it becomes, this is again indicated, the optimal value decreases to 275. Thus, we know that by adding a constraint, the optimal value will never improve, but can at most be the same. Case 3. Adding a constraint which is not feasible. X plus y greater than equal to 12. We know that this constraint is infeasible, yet we add this to check the solution. Minus x minus y is less than equal to minus 12. Adding a slack variable make it minus x minus y plus s4 is equal to minus 12. Forming the initial tableau, we get what is indicated. Pivoting the table 4 times to get non-negative values in the last row and column gives us the final tableau, which has been given. As we see that one of the variables is negative and even the objective function becomes a negative. Therefore, there is no feasible solution and one of the variables is exiting variable. Thus, we conclude that when a new constraint is added to the linear programming problem, the current optimal solution will either satisfy the new constraint, or if the optimal solution does not satisfy the constraint, then there will be two possibilities. The linear program may still have a feasible solution or may not have a feasible solution. This can only be confirmed by adding the new constraint to the problem and checking the solution. Now let us summarize what we have learned so far. Sensitivity analysis is a systematic study of how sensitive the solutions are to small changes in the data. Changing objective function values in the linear programming problem will result in a changed cost row in the final tableau. It might be necessary to add a multiple of row to the cost row to keep the form of the basis. The resulting analysis depends only on keeping the cost row non-negative. Changing the right hand side of a constraint is identical to setting the corresponding slack variable to some value. This gives us the shadow price, which equals the reduced cost for the corresponding slack and the ranges. When a new constraint is added to the linear programming problem, the current optimal solution will either satisfy the new constraint, or if the optimal solution does not satisfy the constraint, there will be two possibilities. The linear program may still have a feasible solution or may not have a feasible solution. This can only be confirmed by adding the new constraint to the problem and checking the solution. By adding a constraint, the optimal value will never improve. It may decrease or at most be the same.